We're continuing a series of lessons dealing with radicals. Today what we're going to focus on is multiplying radical expressions. As it says at the top, it says you can multiply radical expressions by simply multiplying the radicands in each expression as long as the index is the same. And then simplify the radicand as usual. Multiply any integers on the outside, called constants, of the radicand separately from the radicand. So we probably need to know some vocabulary. Generally speaking, when we see radicals, we sometimes see a number out front. We see a radical symbol, and we see another number on the inside. The number out front is called a constant. Generally speaking, it's going to be an integer. It doesn't have to be, but usually the number out front is called a constant. This symbol, very simply, is called the radical symbol. And then lastly, the number on the inside, kind of a cool word, it's called the radicand. When I was younger, I used to think radicand was a really cool word, and I wanted to make it one of my children's names. I just thought Radicand Novinsky was a really cool name, and if it was a girl, maybe making this Radicandy or something like that. Later on, I matured and realized how ridiculous that might be. So now I just think of the inside of a radical, the number on the inside is the radicand. So anyway, that's what we're talking about. So what we're going to do is we're basically going to multiply any of the constants. If there's constants, we'll just multiply them together. If there's radicands, we'll multiply the radicands together, and then we'll just simplify like we've learned to do in the past. So simply for number 1, we see a 3, we see a 2, so we just multiply those together. That becomes our new radicand, which is the square root of 6. We see if we can break down 6. 6 just breaks down into 3 and 2. Again, there's no pairs, so we know that the square root of 6 is our final answer. Okay. Over here, we're going to multiply our outside terms, our constants. So 3 times 2 is 6. We'll multiply the radicands together, and that should give us 18. 6 times the square root of 18 is not our final answer because we can still break down 18. Okay, 18 can be 9 times 2. 9 breaks down into 3 and 3. I look for pairs. There are a pair of 3's, so I'll simply say 6, which was on the outside, times 3, and whatever's left over, that's my 2, goes on the inside. My final answer turns out to be 18 times the square root of 2. If this doesn't seem familiar to you, an earlier lesson really talked just about simplifying radicals, and that actually dealt with having sometimes constants on the outside and kind of just to bring these down, to look for pairs, and to bring the pairs out, and whatever is left over that does not have a pair, that's a prime factor, just goes on the inside to become your new radicand. We're going to continue with this lesson. We'll just simply multiply the constants together. That would give us 15 times the square root of 12. We can break 12 down to 4 and 3. 4 breaks down into 2 and 2. So I'll say 15 on the outside. I'll look for some pairs. There's a pair of 2's. Whatever's left over goes on the inside, so that's 3. My final answer becomes 30 times the square root of 3. Over here, there's kind of a special trick. If you see this symbol right here, that means squared. What that really means is you have the square root of 5 times the square root of 5. If you multiply those two together, that's the square root of 25, which we all know is just simply 5. Notice how this is a 5 right here, and we have a 5 in our problem. It's not a coincidence at all. The symbol out front, the square root, is actually undone by the squared. Okay, what that means is that when I have the square root of 5 and I square it, I can simply jump to the answer of 5 right away, because the square root and the square undo each other. It's kind of like adding 10 and going right back and subtracting 10 right away. That kind of leaves you with whatever you started with. In this case, the squared undoes the square root. They undo each other. Another example of this might be if you have the square root of 17 squared, it's simply 17. If I pick a larger number, the square root of 12,179, and I square that, my answer is just 12,179. So there's really not any work that needs to be shown. If you don't want to, you can basically just say, hey, the square root and the square root undo each other. These are my answers right here. If there's more than just a radical on the inside, we need to make sure that we both square the 7, the constant, as well as the square root. So 7 squared gives me 49. The square root of 3 squared just gives me 3. When I multiply these together, I get the number 147. Notice there's no square root involved in this problem whatsoever. There used to be, but once I squared things, there was no square root. For number 6, we'll square the 2. That'll give us 4. we'll square the square root of 2, which will give me 2. 2 times 4 is simply 8. The next problem, some people make this problem a lot harder than it is. I just multiply my two radicands together. That gives me 100. The square root of 100 is 10. There's nothing remaining when I break this down. I just have a pair of 10s. So I just say, well, here's my pairs. It means my answer is 10. There's not going to be any radical left over at the end. Some people go ahead and try to make this problem a lot harder than it is. They'll just say, well, that's the square root of 5. They'll come down here and they'll say, well, that's, the square root of 5 times the square root of 4. 5 times that would give me the square root of 25 times the square root of 4. They'll say, well, that's 5 and that's 2, so my answer is 10. It seems that all of this is a lot more work than just kind of doing this simple stuff over here, saying, hey, that's 100, square root of 100 is 10. I think it's a lot easier just to think of it that way. Some other people will actually just say, hey, this is the square root of 5. They'll take the square root of 20. They'll kind of break this down into 4 and 5. They'll say this is 2 and 2. They'll come up with an answer of 5 times 2 square root of 5, and they'll not know what to do. They need to realize that basically you still need to go ahead and multiply your radicands and then simplify. I really think this answer is this method up here at the very top is probably the easiest method. Just go ahead and multiply your radicands and simplify later. Over here, number 8, we'll just multiply these two together. That'll give me the square root of 50. I need to continue to break down the square root of 50. 25 is the biggest perfect square that goes into 50. It just breaks down into 5 and 5. So my answer here would be 5 times the square root of 2. I have a pair of 5s. The 2's left over, so it goes on the inside. 5 times the square root of 2. Over here, the square root of 7 times the square root of 7. If you really want, you can change that into the square root of 49, which equals 7. Or when you notice this, hey, there's a pair of these, my answer is just going to be 7. Either way you get it, you can show that the answer is going to be 7. Sometimes using this method, you do get really large numbers, like 768. And what that does is it really tests you to try to pick the biggest perfect square. You can definitely break this down and you get a whole mess of 2's if you really break it down. But if you go ahead and try to pick the biggest perfect square that goes into this, you'd have 256 times 3. If you're really sharp with your perfect squares, you'll just notice that this is 16 times 16, and that in itself gives you 2 pairs, so all you'll have is 16 times the square root of 3. I've seen a lot of students just sort of break this down differently. If they have 768, they'll break this down and say, well, I don't know, how about 24 and 32? They'll break this down into, like 8 and 4. The 4 gets down, broken into 2 and 2, and this is like 4 and 2 again, and here's 2 and over here is another 2. Over here this is like 6 and 4, and this gives us a 2 and a 2, and this gives us a 2 and a 3. And look at all these collections of 2's. It's going to be really tough to kind of keep track of how many 2's there are. There turn out to be, if you count the pairs, turn out to be 8 2's, so that creates 4 pairs. There's a 3 over here, so that gives us the square root of 3. When we multiply this together, we still get this number. But this is a whole lot more work than just recognizing the perfect square. That's one reason we spend a lot of time just focusing on perfect squares, so you can pick the biggest perfect square and then just break that down, and that becomes your constant on the outside. Now, if you can't do that, if you're not good at recognizing that, you can go ahead and break this down, and just make sure to break things down until you find all the prime factors. Number 11, we're just going to multiply these numbers together, so 4 times 3 gives us 12. 48 times 12 gives us 576. 576 breaks down nicely into 24 and 24. So I simply have a 12 on the outside, and since this is a pair, I take the pair out, and since there's nothing left on the inside, I don't have to even draw a radical. A lot of students will say, well, what's left over? Well, there's nothing left over, so don't worry about it. There's just not going to be any radical there. 12 times 24 would just give us 288 as our answer. Over here I have 3 times 6 is going to be 18. And when I multiply 45 and 10, I get 450. I can simply break that down. We'll just say 45 and 10. This becomes 9 and 5. This is 3 and 3. This becomes 5 and 2. These are my perfect, my prime factorization here. So when I look at this, this gives me a pair of 3's that I have to put on the outside with my 18. So bring my 18 down, I have a pair of 3s, I have a pair of 5s, and what's left over is a 2. 18 times 3 times 5 should give me 270 times the square root of 2.